First of all, I want to thank UE Systems for putting this on. This is the world premiere of technology is in this room. Some of the best and the brightest minds in predictive technology are here. Even though you may not realize it, you may not accept it yourself, it is a fact. Because I deal with several different people on several different levels of management and different levels all the way down to the guy that turns the wrenches. And I know experts when I see them, and I see a lot of them out here. A little bit about myself. I retired off the fire department as an arson investigator back in 1986. And I have kind of a type A personality. I can't sit still, and you'll notice I will keep moving here because it's a habit. I cannot sit still. So I decided I needed to find something to do because the days of our lives and as the world turns was killing me. Okay? So I come across a couple of things. I went to work for a company called One Oak. It's a big gas company in Kansas. They have pipeline from Pine Bend, Wisconsin to Mont Belvieu, Louisiana. I was at a refractionation plant in that facility, and we had 93 pumps and motors that I was in charge of keeping running. The plant run 24/7. At that time, they were making $285,000 a day profit. At this time, they're making about $1.4 million because of increases, different things that have been done. You know, it's just $1.4 million a day profit ought to be against the law. But that's what they do. So it becomes very important when you start talking about those kind of numbers that we don't have shutdown. Unscheduled downtime is the most expensive thing they can have. So it's a matter of predictive maintenance. We have to know when a machine is about to go south on us. I was working for them when I started. They were losing 2 pumps a month. Unacceptable, totally unacceptable. I installed some of these programs that we're going to talk about today, and through the help with the fine people at UE Systems and some other companies, we got some technology in there that when I left 6 years later, they were losing 2 pumps a year. The mean time between failure of 2 pumps a month to 2 pumps a year at $1.4 million a day is astronomical, the dollars. And that's the way we have to think about it. You know, it's not a matter of a motor costs $50,000. My plant's not running. I don't care what the motor costs. You get it here, get it put in, because my product is not going down the line. I'm not making any money. So when we're looking at $1.4 million a day, $50,000 for a motor becomes coffee money. It doesn't matter what it costs, get it fixed. And yesterday would be better than today. That's the type of atmosphere we have to start thinking in. We have to start thinking outside of the box, because what's happened over time is we've begun to think about our own little world. And it's like a tunnel vision, okay? These are Del Metcalf on the right does all my marketing. The guy on the left is my grandson. I have another grandson working for me now, and I've found that works the best. A lot of people don't like to work with family. I prefer family because I'm old enough, if they have a problem, I can kick their butt, and I don't have to worry about firing them, okay? That's it. I don't have to worry about firing them because they ain't going to sue me. I will kick their butt. So it works out pretty well for me. Today we're going to talk about ultrasound, obviously. We're going to talk about some infrared, and then we're going to talk about some alignment. Okay. Non-intrusive testing is the safest way to test, if you think about it. We're not going to bother the machine. We're not going to interfere with operations, so that makes them happy. So we just touch it with the instrument or look at it and we run our test. It's a pretty simple operation. Sounds pretty simple. The machine does not need to be shut down. In fact, we would rather have it at a minimum of a 40% load. I want to check it the way it runs, not while it's on vacation. Okay? So if it's in neutral, I'm not getting a true reading. All right? So I want no changes in operation. Obviously, there's less cost in testing because we don't have to shut it down. Okay, with that in mind, then what we need to do is think outside of the box. Since we were children, all of our life we've been trained, if I can't see it, it's not there. Okay? And we prove that every time we see something that bothers us, we cover our eyes. We duck from it. Okay? If I can't see it, I don't have to worry about it. Ultrasound is the same way. Anytime we heard something we didn't like, what do? If I can't hear it, it's not there. I don't have to worry about it. What I'm suggesting to you is there's a lot of things going on in this world that we can't see and that we can't hear. So what we need to do is we need to turn that to our advantage. We need to think outside of the box. This is not a Taco Bell commercial. We need to get outside of that and let our imagination go crazy. Because when we let our imagination go crazy, we start using it to our advantage. You're going to hear things with ultrasound. You're going to see things with infrared that you've never seen or never heard before. We have to learn to interpret that. I have people call me quite often asking me, what does this sound like? What does that sound like? Is it a bad bearing? Or they send me a sound file and say, is it a bad bearing? That's that library that you have to learn, okay? Those things, once you hear them, once you see them, once you know what it is, and once you think outside of that box, you will never forget it. You will never, ever forget it. Your mind never forgets anything. Okay? I can hypnotize any one of you in here and take you back to the 5th birthday, and you can tell me what you were wearing on that day. Your mind never forgets anything. It goes into a file cabinet. Okay? All we have to do is open that file drawer, go to the right file, and I will remember that sound. That's what we have to do. We have to get outside of the box and start using it to our advantage. Okay? In doing that, how can that predictive maintenance help us in our plant? Well, I can certainly tell you if I can predict a failure, I can avoid that failure. Okay? If I know it's coming, I can be ready for it. If I know a bearing's going bad, I can have a new bearing here so that I'm not waiting 3 days or 4 days for it to come from another location. I can have a bearing here. If I know the motor's going bad, I can have another motor here. I can get with operations and say, can you give me this motor on a certain day? And they can adjust their schedule, or I can adjust my schedule to work with operations so that we take that motor down on our terms, not its terms. Outside of the box, we run the plant. The plant does not run us. The biggest problem we can get into is becoming a little fire department and running around the plant putting out little fires. Let's prevent the fire. That's the whole idea. That's what we need to do. So do we operate and think differently? Of course we do. I'm not going to sit here with my feet up on the desk now and wait on a motor to blow up or wait on the phone to come to ring to tell me where I need to run out in the plant and put out this little fire. I run my plant. It doesn't run me. Is it more work than it's worth? I guarantee you, when you start the programs, you're going to have a little more work because you've got all these little fires that are starting out in the plant that you don't know about. They're just waiting to flare up. Okay? So what we're going to do is we're going to find all of those, isolate them, fix the problem. So yes, to start with, your workload is going to go up some. Once you get to the level that you need to be, it's going to level out and your workload is going to be a lot less. We're going to go more into a prevention mode than a rebuild mode. Okay? So, this one kills me. The one on the second one, what did I do with my laser, like Gary? Oh, it's over here. Okay. The second one is the one that kills me. I actually have people, I go in and talk to them, and they say, I've got more work to do now than I can get done. I don't need you coming in my plant finding more stuff for me to do. The first thing I tell that individual, if that's your attitude and that's the mindset that you have, you're too stupid. I don't want to work for you anyway. And that's it. Why would I waste my time on a guy that's got an attitude like that? Because I guarantee you I ain't changing his attitude. So I'm not working for him. I don't want to work for him. Then I have this guy on the bottom. I don't agree with technology. This one kills me. Okay? I started a lot of seminars, and I do a lot of seminars around the United States, and what I do the first time is everybody take your phone out and lay it on the table. They all do. And I look, there's a phone laying in front of every one of them. So then I take my box and I go to the table and I start picking up all the phones. And the guys start screaming, I can't go without my phone. I said, whoa, wait a minute. This is the guy that doesn't agree with technology? I can take this phone right here, right now. I can talk to anybody in the world. I can get in my bank. I can change accounts. I can transfer money. I can do anything I want to do with this phone. 10 years ago, if you were on the road and you wanted to make a phone call, what did you do? Stop and put a quarter in a payphone. Find one today. If you find it, buy it because it's an antique. Okay? Now, with that in mind, think about where we're at today and where we're going to be 10 years from now. That's scary. What we can do today compared to 10 years ago, what we can do today compared to 10 years from now. You buy a computer today, by the time you get it home and get it set up, it's obsolete. Literally, it's moving that fast. So, I take this guy that don't want to give up his phone and I say, now you're not comfortable with this technology we're talking about, ultrasound, infrared, laser alignment. You're not comfortable with that. You're comfortable with a telephone. Anybody knows how to use a phone. So all you're doing is accepting the technology that you're comfortable with. We've got to get outside of that box. We have to think about getting outside of that box. Okay, I have used infrared, ultrasound on every application you see up on the screen. Now, I'm not going to bore you all with going through and talking about every one of them. But if you see something up there that piques your interest, catch me after we get done here and I'll try to explain what we've done or how it happened. Okay? The biggest bang for our buck is ultrasound. It's going to be right here and right here. Safety-wise is over here. Anytime I go to an MCC that's got a whole big line of buckets here that we're going to open all those doors, I take my ultrasound, put the rubber focusing module on it, and I listen around every door before I open them. If it sounds like an arc welder inside that door, I probably ain't going to open it. Okay? So we have the safety thing. We have the arc flash thing that we need to be concerned with. Okay? And at the risk of banging on NFPA, I think the arc flash is way overrated. It's dangerous. It is. And I'm very, very sorry that people get caught in arc flash. I open 25,000 buckets a year. Knock on wood, I've never seen an arc flash. I hope I never do. But you know what? 7 people were killed last year in the United States from arc flash. Okay? Probably 150, 200 were injured from an arc flash. Yesterday in the United States, 1,500 people were killed in car wrecks. Does that mean we're going to stop driving? I don't think so. So let's get real with numbers. We need to think about common sense. When we open a bucket, listen to it first. Even if you don't hear the sound, open the door using it as a blast shield and then move around to the outside of 42 inches. Okay? Common sense. NFPA tries to dummy-proof it, and what we really need to do is get rid of the dummies. Okay? And that's what we're not doing. So we need to think about things like that. Okay, I'll get off my soapbox. On the fire department, NFPA, National Fire Protection Association. I fought them for 20 years because they write the laws so that they can't be sued. And I can guarantee you, we have any electricians in here? Okay, you probably have read up on NFPA 70E. By the letter of the law, if you haven't circuit tested every one of those breakers so that they kick out as they're designed to do, you cannot open that door. Because NFPA says it has to show a sticker on the outside that it has been tested. A 600 amp breaker has to kick at 600 amps. If it hasn't been tested, we can't open the doors while it's energized. Okay? That being said, there's not a company in the world that's going to spend $4,000 a bucket to circuit test 400 buckets in their plant. It ain't happening. So it's kind of a moot subject at that point. Okay, the next one. Infrared thermal imaging. These are some things we need to remember. Heat always flows to cold. Cold does not move. Somebody's welding. You pick up a piece of hot metal. Two things happen. Number one, you decide it don't take you very long to look at it, so you get rid of it. Okay? It's kind of like a guy picking up a horseshoe. Said, you like that horseshoe? Said, nope, it just don't take me very long to look at it. It's hot. The heat flows from the metal into your hand. It burns you. You take a piece of ice, pick it up, put it in your hand. It melts. The heat is flowing from your hand into the ice. Cold does not move, okay? Now, all matter has three states: solid, liquid, vapor. Everything is made up of those three states: ice, liquid, steam. Three states of water, okay? Steel. A steel beam is hard. You get it hot enough, it will melt to liquid. You get it even hotter yet, it will flash to a vapor. It's like 3,700 degrees, but it will flash to a vapor, okay? So we have to remember that. So what we're looking for with infrared is a temperature differential. What is different? Never forget that question. Never, ever forget that question. What is different? Okay? So if we look at this one, straight away I can tell I have a problem here. As an arson investigator, I have an inquisitive mind, okay? What is different here? Two different fuses. We have some electricians in here. When you put in a new MCC, you have a full box of fuses right here. You put 3 fuses in. They're all the same. What is different? What is different there? Different fuses. That tells me already we've got a problem. We blew a fuse at one time or another, so there's a problem straight away. And the other thing is, this may have been the problem because we got a slow blow fuse in there. We didn't fix the problem, we just put a fuse in there to last longer. Okay? Now, if we don't have the infrared picture, we don't know we got a problem here. Don't take a rocket scientist to figure out where our problem's at here. The lighter the color, the hotter the temperature. Okay? Again, loose connection. What is different? We got 3 phases, A, B, and C here. They're all coming from the same load, going through the same switchgear, going to the same motor. They should all 3 be relatively near the same. Well, obviously the situation here, they're not. Okay? Next one. This is another bucket the same way. It's just turned upright instead of laying on its side. But you can see in the center, we definitely have a problem here. Okay? So infrared is now showing us things we haven't seen before. It's going on, we just don't know it. If you don't have this picture over here and you look at this, you don't even know you got a problem. All right? Variable speed drives. How many people got variable speed drives? Everybody's got them, okay? These are notorious for having problems. The reason why, when you energize a wire, it warms up. As it warms up, as everything else does, when it gets warmer, it swells. When you shut it down, it goes back to its natural state. So now when you're ramping your variable speed drive up and bringing it back down and ramping it back up, it's swelling and shrinking and swelling and shrinking. That screw doesn't move. So actually what's happened is swell, shrink, swell, shrink. We've got a gap in there now. The power has to jump across that gap. How many of you can remember, some of you look old enough in here to remember, when I used to have my old car, I'd set my points on a little wider gap because I'd get more power and more hotter spark at the plug, because it takes more power to jump across that gap. Okay? The same theory is happening right here. More power, more resistance, more heat. What is different? Doesn't take long to figure it out here. Okay? Look at this one. That screw right there is loose. Look what's taking place here. This is a critical machine. I'm from Hutchinson, Kansas. This is a 500-bed hospital. This is the controller, variable speed for the air conditioner, 200-ton air conditioner that runs the entire emergency room. Two things we have to think about here. The first one is doctors don't like to sweat. And they're pretty adamant about that. The second thing is nurses like it even less. Okay? So, what we have to do here is think about what are we going to do if we lose this air conditioner? All right? I found this on Friday, the Friday before Labor Day weekend. Early September. Okay? Pretty hot out, pretty warm out. I called Bill and I said, Bill, we got to shut this machine down. He said, you are out of your mind. Remember, doctors and nurses don't like to sweat. I said, well, if we don't shut this down, somebody has to make a decision here, because if we don't make a decision, it's going to. When is it going to fail? I'm thinking about Saturday morning, 2 o'clock in the morning. We don't have any staff here. What staff we do have is out at the lake, and they're probably drunk. So now I got to call them into work. We got to get this thing done under emergency conditions, so we're not doing things the way we should do them. So it's a fire department putting out the fire. I told Bill, let's shut the plant down. Let's shut this machine down. He said, no, we ain't doing that. I said, okay, do me this then. Go to the thermostat and turn it as cold as you can turn it. He said, what's that going to do? I said, well, it's going to load that air conditioner up. But I want it cold enough in that emergency room that the nurses are wearing sweaters. He said, well, again, what's that going to do? It's going to buy us some time. Because I can come out there at 8 o'clock tonight. After the sun goes down, we can shut that unit down, because we've built some time because it's so cold in there. We also have used the sun to our advantage. After it went down, it's not going to heat back up as fast. That buys us some time to shut this down and fix it. Okay? So we did that. We shut it down and fixed it. Right here's the loose screw at 369 degrees. I don't know why it didn't melt down before, but we shut it down, took that wire out, cut it off, cleaned insulation back, put it back in, tightened it up, tightened up all of the rest of the wires to make sure they were tight, and we started the machine back up. 20 minutes of work. After we had it locked out, tagged out, 20 minutes of work, okay? Here it is now. An hour after it had been started back up, that temperature is 138 degrees. We run the plant. We did not allow it to run us. Okay? That's the difference. Now, this contactor did have some damage from overheating. But you know what? In November, when it's cold out, we're not running the air conditioner anyway, we go back and replace that contactor. Now, is this a lot better, or would it have been a lot better at 2 o'clock in the morning? That is predictive maintenance, okay? Some of the problems that we can detect with ultrasound and infrared. Soft foot. Does anybody not know what soft foot is? Okay, what happens when we set a motor down on a skid or down on a base? That base has been machined so it's all level, okay? When we set the motor down, the feet of the motor have also been machined so that they're all level. How many of us have sat at a table that has one short leg on it and it wobbles, okay? So what happens if we bolt that down or we force that motor down and they're not all milled the same? We actually force one leg down like this. What we've done is we put a twist in the motor case. We put a twist in the motor case, we're going to start seeing hot spots in the motor, okay? So we can see that. We also can hear that with ultrasound. All right, misalignment. I've had people tell me that you can't see misalignment, you can't hear misalignment. I'm telling you that you can. I do it every day. My staff does it every day. They say, you can't tell misalignment with ultrasound. I'm going to show you, you can. Okay? Greasing problems, a real pet peeve of mine. We've had some demonstrations on greasing and lubrication. This one here is a real pet peeve of mine, and we'll talk about it. And then mechanical looseness. The first thing we have to do, though, before we can do any of this, is we have to make a motor ready for service. How many of you, when you get a new motor in your plant, it's sitting here on the crate, how many of you pull the grease tubes out of the motor to make sure there's grease in them? Not one hand. I'm telling you, they are empty. You go back to a new motor and pull that pipe out of there, I would almost bet you, my firstborn son, that pipe is empty. Because the motor company doesn't know if you're using moly-based grease or poly-based grease. So they don't put anything in there because moly and poly are like twin sisters. They don't get along. Okay? What happens is they'll form an acid that will eat the race out of your bearings in 3 to 5 years. So the only grease that's in that bearing is the grease that was put in at the factory, and that's to maintain that bearing during the shelf life before it's installed. That is enough grease in that bearing to actually run your motor for about a year. How long is the warranty? So we got enough grease in there to go a year to get us just out of warranty, and then we're going to buy a new motor from the same motor company that just shafted us on the one that just failed because it wasn't greased. So you got to pull the grease tubes, pump your kind of grease in there until it comes out, put the tube back in, give it 3 or 4 good shots to make sure we have grease in the bearing. If we put a motor in and it fails in a year, we wonder why. We shot ourselves in the foot. It wasn't ready for service. Okay? The next one, a shaft run-out test. How many people run a shaft run-out test on a motor? New or rebuilt? 1, 2, 3. Very good. Very good. Let me tell you what happens. And I started this in Boeing. Boeing is a pretty good sized company. They weren't doing it. Okay? So I go to Gary here, and Gary calls me and says, I need a 100 horsepower motor. I said, okay. So I take it to Gary, and he sets the motor down on the bench, takes a dial indicator, puts it on the shaft, runs it from the keyway all the way around to the other side of the keyway. If it moves more than 0.003 of an inch, you do not accept the motor. Reject it. Send it back. We're going to have to align this motor to within 0.003 of an inch. If it's 0.005 out over here, when you roll it to the other side, it's 0.005 out that way. We're 0.010 out already. There's no way we can align this within 0.003 if we start out 0.010 off. So you reject that motor. So the motor company takes the motor back. They put it on the shelf. The next day you call and you want a 100 horsepower motor. What motor do you think you're going to get? You're going to get his reject, because they're not going to send it back in. They're going to send it to somebody that doesn't test their motors. We have got to run that test. We've got to run that test to protect ourselves. I'm not an experimental field. I need reliability. And if I don't run that test, I'm shooting myself in the foot again, okay? Bench vibration test. I run vibration for one oak for about 6 years. I don't run vibration anymore. I can get better, faster, more accurate results with ultrasound than I can with vibration. I'm not saying vibration is bad. I'm just saying I can do it faster and quicker and get the same results with ultrasound. Now, I want that bench vibration test though, because I know if I go out on that spectralizer and I see at 140 to 146,000, I start to see the 4 spikes from the 4 stages of bearing failure. I know about what they are when we put it in. That's kind of a baseline for me because I just happen to use the same FFT scale with ultrasound as we used with vibration. That's what your spectralizer is, okay? The last one is one of the most important, and nobody does this. We put a new motor in, we hit the start button, and we're up and running. You know what happens? That says start on it, that button. You know what that actually starts? It starts the failure mode. Think about that. It starts the failure mode. As long as that motor's sitting there and not running, it ain't going to fail. But the minute you push the start button, the failure mode starts. It's up to us to see how long it is. Okay? So we should take an amp draw when we first put that motor in. When I put that motor in, brand new, under load, normal running conditions, I was pulling A, B, C phase, 6, 6, and 7. I document that, and I document everything I do. Everything. I've got 28,000 pictures on this computer up here. I never delete nothing. Okay? 8 months down the road, I start to have problems with this pump. I take another amp draw. Now I'm at 12, 12, and 18. If I didn't take that amp draw to start with, I have nothing to compare to. I have no baseline. I don't know I even got a problem. As far as I know, 12, 12, and 18 is normal because I didn't take that amp draw to start with. I didn't set my program up for me to run it instead of it running me. These are things that have to be done. Okay? We grease a lot of motors. My company does a lot of greasing because we grease with ultrasound. We're going to get into that. These are things that we require of a company when they put a motor in. If they don't do this, we don't grease their motors. It's that simple. I'm not going to accept the liability of greasing their motors if they're not going to have them ready to go when they start. Okay? So, this is a point that a lot of people have asked me about, and I wanted to throw this in here just so everybody would understand. Terminology, a lot of times we get lost with. So when I talk about a bearing or I talk about a machine, I start at the fan end of the motor. That's the motor outboard bearing. The motor inboard bearing is the shaft end of the motor. Now you hear drive in, opposite drive in, shaft in, fan in, you know, all of that different terminology. If we would just standardize to motor outboard, motor inboard, gearbox inboard, gearbox outboard, pump inboard, pump outboard, it's pretty easy. The pump outboard, that's the impeller out on the end. It's kind of like the fan on the other end, isn't it? So what we've done is we started at the fan end of the motor and we just took the power stream right through the machine. And it makes it a lot easier. Now, if Peter from London over there calls me and says, Chuck, I'm having a problem with this motor outboard bearing, I know exactly what bearing he's talking about because we're on the same page with terminology. If he calls me and says, I have an opposite shaft end bearing that's giving me a problem, I'm thinking, what are you talking about? But when he says motor outboard bearing, I'm there right now. No question about it, okay? This is very important. So that's something we really need to pay attention to, okay? Next, yes? Gearbox, follow the pattern, okay? I have a motor here, a gearbox sitting here, and a pump here. Input side, exactly. Now, your gearbox is going to have, it depends on if you have an intermediate gear or if it's just a direct drive. You have A shaft and B shaft, or you have A shaft, B shaft, and C shaft. But it's gearbox inboard A shaft, outboard A shaft, inboard C shaft, outboard C shaft. You see, you have an inboard side of the gearbox and an outboard side of the gearbox as the power goes through the machine. Okay? All right, soft foot. Here's one right here. Notice remember I said we put a twist in the case? This is an example of it right here. That's the hot spot that's going to show up with infrared. We have a 10,000 soft foot under that foot right there. That is a 300 horsepower motor running on 2300 volts and costs about $25,000. And we're wasting the motor because we have a 10,000 soft foot that's not been corrected. This was found with ultrasound. Can you drag the spectralizer over onto the screen? Hello. Okay, we need to go up to File. May have to drag it. Soft foot before. Should be down at the bottom of the list. Okay, play it. Listen for the surge. Can everybody hear the surge in that? Okay, what we done was we corrected the soft foot. All right? Now, remember we've got one foot that's 10 thousandths, right? So logic would say we let that foot come up and put a 10,000 shim under it. But remember the table that rocks with the short leg? Okay, instead of putting a wedge underneath one leg, what we should actually do is put a wedge underneath the two opposite legs. So instead of a 10,000 shim going under one corner and letting the motor sit there already crooked, we put 5 thousandths over here and come to the opposite corner and put 5 thousandths there. So we stop the rock. Okay? So that's what we done. Okay, play the next one. It should be soft foot after. Surge is gone. That was recorded with a 10,000. Okay? So the soft foot is there. You can hear that. Now, the thing about it is, okay, you can drag that back off. I actually seen it with the infrared. And I thought, whoa, what's different here? Where's that question? What is different? Right there it is. That's what's different. So then I got my ultrasound and I listened to it. That's when I hear the surge. There shouldn't be a surge in there. Okay? That's when I heard the surge. Then we started, it raised a flag. I got to find this problem. What is the problem? That's what it was. So we resolved that problem. Okay, next slide. I guess I'll do it here. Up, you got to come back to this screen and click in it once to turn it back on. There we go. Thank you. Misalignment. Before you can even attempt to correct a misalignment, you have to do away with the soft foot. Because remember, we're twisting that case. So what it's going to do is it's going to affect that shaft out there on the end with that twisted case. So we have to correct the soft foot before we can begin to think about correcting an alignment. Misalignment, it's been our experience in the field for about 10 years that misalignment is the number 2 cause of premature motor failure. I have people just amaze me. They measure the top of the coupler. Yep, 3/4 of an inch. Yep, 3/4 of an inch. Using a tape measure. I have yet to see a tape measure that will measure thousandths of an inch. Okay? I've actually seen them take 2 framing squares, put them on the side of the coupler. It comes out and the L's go this way. And they, yeah, that's pretty close. And they take it and run with it that way. And then wonder why their motor fails. Misalignment is 2 shafts like this, and you're actually trying to turn a hinge over. All the stress goes back into the bearings, okay? So we cannot allow that to take place. So what is misalignment? Shaft to shaft has to be collinear, 0 to 0. They have to turn the same. They can't do this, okay? How does it sound? I have 4 points on my machine. I have a motor and a pump, okay? If I take an ultrasound reading here and I have 30 dB on the motor outboard bearing, The motor inboard bearing is 48 dB. The pump inboard bearing is 52 dB. The pump outboard bearing is 37. Where's the difference? The two inboard bearings are significantly louder than the two outboard bearings. Why? Shouldn't be. Okay? First indicator of misalignment. All the stress is going into those bearings. You got more stress, you got more friction. You got more friction, you got more noise. What else does friction cause? Exactly. So how do I confirm a possible misalignment? Okay? Infrared would be a great way to check it. Okay? Look for the heat. What kind of damage can it do? Well, it certainly shortens the life of the motor if we're running all that stress through those bearings. Is it a hard test? We just done it right here. And it takes about that long. You put it on the outboard bearing, set your volume or your sensitivity, get that bar up above the E, which is one I insist on, and I'll show you why in a little bit. I don't move the sensitivity from there. I move to the next bearing, the dB's higher. I move to the next bearing, it's higher. I move to the last bearing, it's back down again. It's that simple. That test has been completed. Can it add to the bottom line? If I can take a 5-year motor and make it run 10 years, I guarantee you it adds to the bottom line. Okay? So it's pretty simple. This is what we have for misalignment. If you notice the bottom of the motor, here we see all 4 feet. That means we're looking down onto the motor. Here we see just one set. That means we're looking at it from the side. Okay? You can see the types of misalignment we have. Parallel and angular misalignments. Okay? This happens every day. Every day. This is what it usually feels like. Okay? This motor over here is got 4 bolts holding it down. That's it. And the coupler. That's it. The pump out on the end, it's got all this big piping and all this bracing and all this stuff. It don't shake a lot. But that motor's out here jumping all over everywhere. Okay? That's another indication of misalignment. Now we've got 2, right? We got the motor jumping around and we got the louder bearings. Okay? So let's move to the next one. We look at this motor. This motor to the eye appears there's no problem at all. We take an ultrasound reading. The 2 inner bearings are louder than the 2 outer bearings. I pull my camera out and look at it. Doesn't take a rocket scientist to understand this picture. Okay? Right away, I have now combined 2 technologies to prove one point. That's the importance. That's the importance. I could take a vibration on this and find I would have a big spike at 1.5 times the turning speed, which indicates misalignment. Okay? So it doesn't take very long to figure this out. The idea is we're thinking outside of the box. We're hearing things we've never heard. We're seeing things we've never seen. And we're using it to our advantage. Okay? Let's look at this. We realigned this machine. This is what predictive maintenance, This is the way it was when we found it. Look at this, 91 thousandths out of alignment. This one must be the one they used the 2 squares on, or the tape measure. But you can see after we aligned it where it's at now. Those are not thousandths. Those are tenths of a thousandth. This machine was to align to less than 1,000th. When we first started on this machine, I could take the coupler and I could barely turn it over. When we got done, I could lay my hand on the top of it, let it fall off, and watch the motor coast to a stop. That much stress was taken out of it because of the misalignment. How much easier would that motor run if it's aligned properly? How many less amps would it pull if it's aligned properly? So now we're not only saving the machine, but we're using the energy efficiency aspect of it. Okay? Here's another one. You look at this and it doesn't appear there's a problem at all. No problems here at all. Okay? Infrared will tell you right away that there is a problem. That bearing should not be that hot. That pump bearing should not be that hot. Again, inboard bearings. Okay? Here's the misalignment we've done on that one. Another one. This is a Martin-style coupler, and these just kill me. Martin-style couplers. They tell you that that coupler right here will take out from 10 to 15 thousandths misalignment. I tell you, why, if we're going to align it, would we be satisfied with 10 to 15 thousandths? I think there was a statement made in one of the presentations yesterday. That's good enough. Good enough is never the right answer. Good enough never happens. Okay? If I've got the lasers on there, I just will take it on down where it belongs. How many of you have taken a piece of wire and take it back and forth like this till it breaks? Gets hot, don't it? That's what's happening to that piece of rubber in the center of this coupler. Those hubs are sitting here doing this, and they're actually heating that rubber up. There's no other reason for that rubber to be hot. You see on the sides, the coupler's not hot, or not that hot, so why would the rubber be hot? Other than the fact that it's just sitting there beating it out. Okay? Misalignment. You can also see how when we realign this one right here, dead center. That can be attained. That can be done if you do it right the first time. And you take the time to do it right. Now, this machine goes down. I got management back here chewing on my backside. Let's get it done. I got to get it up and running. And I'll turn around and tell them, and I'll tell you what, it'll make them mad. Hold it. You give me time to do it right the first time, I only have to do it once. If you hurry me where it's in emergency conditions and I get in a hurry and I start putting my hands in where they don't belong, or I start taking shortcuts and then I come back without a finger, it's going to be a lot more expensive to do it that way than it is if you just allow me the time to do it right. And I only have to do it once, instead of doing it wrong in a hurried fashion and have to come back here in 6 weeks and do it again because the motor failed. So the point is, take the time to do it right the first time. This machine appears to have no problems at all. This one here is a classic. Appears to have no problems. We look at it with infrared. The sound, the ultrasound, told us it was misaligned. We look at it with infrared. Obviously, look at that pump. That pump is short for this world. 3 days after we run this, we give them the reports that day. 3 days later, they decided they didn't want to shut it down. They're not going to take care of it. That night, it failed. And it shut the plant down. Shut the entire plant down because they didn't want to take care of the problem when they had the opportunity. This is one that some guys wanted me to throw in. I showed them last night, so I'm going to throw this for Stan in right quick. This motor here was like that little cartoon we seen a while ago. It's shaking and jumping around, okay? So they decide they're going to fix that vibration in it. So what they do is they put vibration dampeners in it, under the feet, under the skid, all the way around it, okay? And they done a good job. They put a lot of them in. But what they also done was they insulated this motor from ground. Look here. Those are rubber expansion joints to keep the vibration from working on the piping, okay? Right here, that's PVC. So everything they've done to this machine isolated it from ground. It's a variable speed drive, okay? So now what they've done is by isolating it from ground, actually they were having a rotor charge up. It started fluting the bearings in the motor, so they put ceramic bearings in it to stop that. Now, because it's still isolated from ground, it's going from the motor through the shaft, through the coupler, through the blower, out to this bearing right here, and that bearing on the outside failed. And they wondered, well, we put ceramic bearings in it, why did it fail? Well, it's got to go to ground somewhere. Because that's a thrust bearing on that end, the film or the grease film or what little bit of insulation there was is a lot less there because of it being a thrust bearing. and the configuration of the bearing, it went to ground quicker there. Okay, now the killer. The real killer of this is that motor was shaking around the way it was. We checked it. It was 65 thousandths out of alignment. That's why it was shaking. So they put rubber feet under it to try to solve that problem, and they created a bigger problem than they had to start with. Okay? We took the rubber feet back out from under it, aligned it the way it should be. That was 2.5 years ago, and this machine still runs today because it was aligned properly to start with. So sometimes we get into a rut, or we jump to a conclusion, and we don't really know what's going on without checking out all the factors. And that's exactly what they done here. They created more of a monster than they had to start with. But they never checked everything to start with. So we'll move on. This is the lasers that I use. This one here is for the shafts. These are for pulleys. And I can align belts and pulleys on 3 different planes with those. Okay? So testing for misalignment. Testing for misalignment is very simple. We just done it here a while ago, okay? We want to confirm it, okay? Can it save the bottom line? Obviously, it can add thousands and thousands of dollars, okay? So, we move on. If misalignment is the number 2 cause for premature motor failure, what's number 1? I'm sorry? Improper lubrication. Thank you very much. So many times I hear lubrication. That's not always it. Because sometimes it's better not to lubricate it at all. Because we have people in the field that say, you know what? If 3 strokes is great, 6 strokes ought to be freaking awesome. And they're killing themselves by doing that exactly thing. It's kind of like the arsonist when I was investigating fires. If 1 gallon of gas makes a pretty good fire, 50 gallon of gas ought to really make a blower. We can't operate under that theory, okay? So what happens is, how much grease is enough? How many of you have taken your grease gun at home and went squirt? How much grease is that? Nobody knows. Nobody ever checked. I would suggest that you all go back and get a 1-ounce shot glass. Now, is there anybody in here that doesn't know what a 1-ounce shot glass is? Okay. Everybody pretty well knows what that is. Now, if I take my grease gun and I stand here and I go, it takes 10 strokes to fill that shot glass, okay? The next time I go grease this motor, it takes 3 strokes for me to quiet it down. I just put 3/10 of an ounce in there, didn't I? Document it. Document that. Right there, it's got to be documented. Because 6 months later, I'm going to come back when that motor's making noise again, and I put 5 strokes in it. I look back, whoa, it only took 3 strokes a while back. It takes 5 now. It's going downhill. Write it up. Now you have a way to measure how much grease you're putting in there. Didn't have that before. Okay? Next thing, what kind of grease are we putting in it? What grease do we use? If you're using poly, that's the blue, then I would suggest, don't make any difference what grease you're using, I would go back to my plant and I would buy a brand new grease gun. And I would paint it hot pink or day glow orange. Something that's really loud and bright, okay? Point being, that grease gun is used on electric motors. It does not touch anything else. I hate to see somebody take a grease gun and put it on a pillow block bearing after they wipe all the dirt away from it and contaminate the tip, and then take it and put it on my $20,000 motor and pump that dirt into this bearing. Quit doing that. Buy a hot pink grease gun. If I see somebody grease an electric motor with anything other than my hot pink grease gun, there's my grandson, I'm kicking his butt. Okay? If I see any grease gun on that motor other than that hot pink one, and I better not see that hot pink one on this pillow block bearing contaminating the tip over here. I don't want you pumping sand into my motor. A pillow block bearing, we can grease that like it says. How often do we grease? A pillow block bearing, we grease it till we see grease oozing out of it. There's that farm mentality. We're not greasing the bearing. All we're doing is purging the dirt out of it. Okay? So, what type of grease? We talked about that. How often do we grease? Book says every three strokes every 6 months? Timely intervals. I'm telling you, throw the book away. Throw the book away. If you start greasing with ultrasound the way you're supposed to, the new technology, we can throw that book away. If I have a 100 horsepower motor sitting right here, it runs 24/7. I have a 100 horsepower motor sitting right here that runs 2 hours a week. How in the world can I grease them both the same? Like the book says. One's not going to get enough, the other's going to get way too much. So if I grease with ultrasound the way I'm supposed to be doing now, what is different? I listen. The ultrasound will tell me if it needs to be greased. It will also tell me when it's got enough grease, so I quit greasing. If it don't need grease, I don't grease it. If it does need grease, I grease it real slow until ultrasound tells me it's got enough. Then I document how much I put in there. Was it 0.2 of an ounce or 0.3 of an ounce? Remember our way of measuring. Okay? So, with that in mind, then let's grease a motor. Oh boy, what is this? Does anybody recognize this? Over-greasing a motor. Let me tell you what happens. And we got some electricians in here, and I'm glad of that. I'm going to have to hurry here. I'm glad we do, because contrary to what most people believe, electricity doesn't go through the wire. It goes around the wire, okay? That's why we take an amp probe and clamp around the wire and measure that magnetic field. That's how many amps we're pulling, okay? So, by going around the wire, the other thing is insulation is not put on the wire to keep you from getting shocked. It's put on the wire to direct the flow of current the right direction. Now, if a motor, all the windings inside that motor are baked with varnish. That is the insulation, okay? So that's directing the flow through the motor the way it should go. One magnet chasing another one. That's all that makes a motor turn, okay? Now, if we over-grease it, what happens is the balls push the grease to the outside, and now we have a tunnel in that bearing for those balls to run in. And we keep greasing, and the grease gets out into the windings. And then the grease dissolves that baked on varnish, so now we got current going all different directions instead of flowing through the motor like it should. So we have a weak magnet and a strong one and a weak one, and so our motor loses power. It starts to heat up. What's the first thing we do? You put grease in it. That's what killed it. But that's what we do every time. Even when we see this and we know it's over-greased. I asked this guy, how much grease you put in that motor? He said, Chuck, it's a 25 horsepower. I said, yeah. How much grease you put in it? He said, it's a 25 horsepower. I put 25 strokes in. I thought to myself, what do you do with a 600 horsepower motor? Pump a 55-gallon drum in there? That's the kind of people we have in the field doing that kind of logic. We can't, what did I say a while ago about getting rid of the dummies? It's amazing. It's amazing. Okay, so let's look at the next one. Here we go. Again, that tunnel that the balls are rolling in becomes an insulator. It gets hot, it breaks down the base, moly or poly, and then it starts slinging all the oil to the outside, centrifugal force. And it starts leaking around the end bells. Classic sign of over-greasing. Okay? Remember the motor, 25 strokes, 25 horsepower? You think I was kidding you. That's it. No wonder the motor's losing power. No wonder it's getting hot. All right? It's amazing what we find in the field when we start looking at stuff like this. That one's not bad. Look at this one. You know, after about the 7th tube of grease, somebody ought to be asking where it's going. And the other thing that bothers me is, look here. It's a shielded bearing. You couldn't get grease in it if you wanted to. then why does it have a grease zerk in it? I talked to the maintenance man. He said, well, we needed to grease that motor, so there's a pipe plug in there. So we pulled it out and put a grease zerk in it. And we greased and greased and greased, and we never did get it to quiet down. I'm thinking, oh, here's one of them dummies we got to fire. The pipe plug is put in there for a reason. That's telling you it's got shielded bearings in it. Don't pull it out and put a grease zerk in there. In my plant, I will not accept a motor that has shielded bearings. Okay? If you're not greasing with ultrasound the way you should be, you can use shielded bearings, because what it's going to do is keep you from over-greasing that motor. That's exactly why it's there, to keep you from over-greasing your motor. Okay? So let's grease a motor. This is a 200 horsepower motor running this big pump that's pumping 1,500 barrels per hour of propane that's boiling at 600 degrees. Now, if we lock this motor up, that impeller is turning so fast and so hard, and there's so much inertia. When that motor goes, that impeller is going to twist the shaft off in this pump, and it's going to come through that housing about right there. Now we have all of this propane out in the air, and it expands 242 to 1. 1 cubic foot of liquid expands to 242 cubic feet of gas. Gas is what burns. It fills the river in Hutchinson, Kansas, and follows the low areas, all the river, all the way down to Wichita, Kansas, and finds a place to ignite. Somebody's hot water heater kicks on, lights that, and it flashes all the way back to the leak. In about 10 minutes, we've covered Reno County in about 4 foot of propane. Cannot happen. Cannot happen. It is not an option. So we grease this motor with ultrasound. Bring the spectralizer back over there, Stan, and we're going to grease this motor. Go to File. There you go. Now you can drag that down here where we can see it, or you can do it. It doesn't matter. We want bad bearing, or the grease bearing number 1. Bearing dry, right there. Nope. Yeah, play the dry one. This is the bearing that's dry, okay? Listen to the choppy sound in it. You're going to hear it. It's going to sound like propane. Plastic, potato chip sack, cellophane is what I'm trying to think of. Crackling, okay? Hear the crackle in it? Okay? Play the next one down now, Stan. I think the next one down is the bearing being greased. Listen for the change, okay? Listen for the change in it. The spectralizer doesn't concern me as much as listening, okay? That was done, that was recorded with the 10,000. I'm here to tell you today, there is no reason anyone should ever over-grease another bearing. That is the proof. That is predictive maintenance. You go through your plant, I check 400 bearings in a plant, I might grease 2. Because I'm not going to go through my plant and put 3 strokes in all 400 bearings. It's crazy. Let's do it the way it should be done. Accept the new technology. Listen to what your equipment is telling you, and do what it advises you to do. Okay? Now we have several examples here of motors, and I'm not going to. Here's that 600 horsepower motor. It's got a 55-gallon drum of grease in it. Okay? So you see what happens when we start thinking about bearings. The thing about it is they're all going to be the same. This motor turns at about 1700. The compressor that it's driving turns at 13,000. So again, it's not an option for it to lock up. We're going to lose it, okay? This one, a 200 horsepower motor, this little gearbox right here is pretty hard to see. It's a Sundyne gearbox. It's about this tall. Cost $250,000. It turns an impeller that's about this big at 27,000 RPMs. It's a hydrogen gas compressor. If one drop of liquid hits that compressor, this motor crashes. The whole thing, because of the difference in molecular weight of the hydrogen gas versus the liquid, when it hits that impeller, it'll crash it. Literally, I've seen the case fly apart. So that's not an option. At 27,000 RPMs for that motor to just go is not an option. We cannot do that. So that's why we use ultrasound for lubrication. Okay? What should a good motor look like under infrared? Here's a perfect example. Notice the center of the motor is warm, the inboard bearing here is cooler, the outboard bearing here is cooler. If I look at an electric motor with infrared and I ever find either one of these bearings warmer than the center of the bearing, I have a bearing problem. I don't know what it is yet, but I do have a bearing problem. Think about this. When that motor started up and it's up to speed, it rises to magnetic center. That rotor inside there rises to a magnetic center. It will also move axially, lengthwise, to magnetic center. So once our motor's up to speed, then our bearings are not even loaded. The magnetic center is what's driving the position of the rotor, not the bearings anymore. So there's no reason for the bearings to be hot. No reason we should ever have a bearing hotter on either end than the center of the motor, unless we have a problem. This happens to be a belt drive. Do I have the belts too tight and I'm pulling that bearing over into the race and it's heating up from the friction on that one side? Which brings us to another point. The junction box is on the other side of this motor. When I send the motor into the shop, I want my bearings marked. When you pull a bearing out of one of my motors, I want the outer race peened on the same side as the junction box. Now, when you send my motor back to me, those bearings better come with it. Because if they don't, I'm not accepting the motor. When I get those bearings back, I put them in a solvent tank, clean them up and get them all nice and shiny, and then put them in a chop saw and cut them in half. Now, where that peen mark is tells me the exact position of that outer race. The inner race turns, the outer race is stationary. If I look, right there's a peen mark and this whole side is galled out and it's a belt drive, what's that telling me? I probably have my belts pretty tight there if I pull that bearing over to that side. What happens if this side of the race is bad and this side of the race is bad? There's a chance I had my bearing cocked in there, okay? So now, instead of just throwing bearings at a problem, let's try to find out what the problem is. Prevent the problem from happening again, okay? So those are some things that I insist on. This is the formula. I mentioned earlier that I can do it. I can get the same results quicker, better than vibration. This formula allows that. This is in your spectralizer, okay? What we do is we take, for an outer race, we take 4% or 0.4 times the number of balls in the bearing times the turning speed. Divide that by 60 to get us back to hertz. Whatever that number is going to be the fault frequency of the outer race on that bearing, okay? And 0.6 is the inner race, what have you. Bring up the one that shows the fault frequency there right quick. Up the other one. You may have to go down here and get the Excel spreadsheet. Yeah, there we go. Now drag it over here. This is a spreadsheet that I put together that works that formula for you. Okay? So drag that back off, Stan, and bring the spectralizer over. And let's play the bad bearing. Remember this bearing, because it's going to come back to us here just shortly. Go to File, play the bad bearing. Listen for the bass sound in this bearing. You hear the bassy sound in it? Okay. How many of you in here are old enough to remember when we used to ride bicycles, we used to take a playing card and bend it around the spoke and put a clothespin on it so that the card would hit the spike, the spokes in the... The faster we rode that bicycle, the more it sounded like a motorcycle, didn't it? Okay. Picture this. If you have a pit in the race and you have the balls going around, this is your spokes. The balls is the card. It's banging on the other side of that pit. And it's doing it 1,700 times a minute. One ball times 8. 8 balls. There's no way we can hear that other than that hum. That's that bass sound that we hear. So, Stan, put me a harmonic cursor. Well, bring it back. Put me a harmonic cursor on this one right here. Now, here. Just go to the top of it up there. Right there. Hold the shift key down and hit enter. Okay. He's showing 109, but he's not on it, right? So if we go down here, this will let us toggle. Bring this down. Bring it down until, and watch it move over. Keeps going, keeps going. Keep on going. Down, buddy, down. No, do it right here. Go down. Why are you not going down? Oh, he's a lot smarter than I am on this. Okay, take it on down. Whoa, right there. We're on every one of them, aren't we? We hit. That's the ball hitting that pit. Okay? And it's doing it at the same formula we used a while ago. Remember that number. It's 91. Okay? Bring the spreadsheet back up, the Excel sheet. This right here is the spreadsheet that he's starting to bring up. Okay? So now, if I know this is a 6313 bearing, it's got 8 balls in it. The tag on the bearing, the motor says 1735. So if I go to the 0 there, which is the speed, nope, this one over here. Right there. That's where I put my speed in. So 1735 and hit enter. That tells me that 92.5 is the fault frequency for the outer race on that 6313 bearing. What was our number? 91, right? Okay, so if it's 91, what's changeable on this chart? There's nothing that we can't change the number of balls. I mean, that's pretty obvious, okay? So all we have left is speed, right? So let's drop that speed to about 1725. Okay, we're getting a little closer. All right, take it to 1710. Bingo! What it's just told us is we have an outer race failing on that bearing. Okay? Yes. Now, the other thing, a very good point. It's overloaded. Why? Let's go back and think about what we've talked about here today then. If I take infrared and look at that bearing, it's probably going to show hot, right? If I take an amp load and compare it to when the motor was put in new, I'm probably going to show higher amps than I were earlier, okay? If I look at the tag speed and see that I'm only turning 1710, why? Is it possible that my bearing is in such bad shape that it's putting more drag on the motor, it's calling more amps, it's heating up? You know what? If it sounds like a rattlesnake and it looks like a rattlesnake, don't pick it up. It probably is a rattlesnake, okay? Right here, if the bearing sounds bad, infrared shows it looks bad, the speed shows it's bad, we got 5, 6 indicators here that we got a bad bearing. All right, so let's take this off, Stan. Take that off. And so, with that in mind, I don't know what I've done with my, I'm lost. Here it is. With that in mind, let's look at that motor. This is the motor right here, okay? Here's the heat that we talked about. We know it's heating up. It's shaking. The outer race is showing a failure. The motor slowed down. I talked to Lowry and said, what are we doing? He said, this is a 100 horsepower motor. We can put new bearings in it for about $3,000. All right? A new motor is going to cost us about $6,000. It takes 10 days to a week to 10 days to get a new motor here. And I told him right away, you're dealing with the wrong motor company. I don't even buy motors anymore, but I still have enough connections that I don't care what kind of motor you need. I can have it at your plant at 8 o'clock tomorrow morning. It might cost you $50,000. But at $1.4 million a day, you don't care. I can get it there. Okay? The reason why I can get it there is because I know the motor companies that I used to deal with. When I dealt with them, I told them, look, I'm not keeping any inventory in my plant. How many of you have spare motors? How many of you go out every 30 days and spin the shaft over? What happens? The motor's sitting here, the rotor is sitting down on that bearing. Trucks go by, trains go by, planes fly over. It's sitting there shaking. It's sat there for a while now, and it's wore flat spots in there, and now you put your motor in that was brand new on the shelf for a year, and you wonder, why did it fail in 6 weeks? Hell, it beat itself to death sitting on the shelf because we didn't spin it over. What's the keyway on there for? We got 12 months in the year. January, February, March, April, May. I walk through the inventory shop and I can tell what month it is by looking at the shaft on the motor, because they are spin over and stopped back at that month. Okay? Simple little PM program that costs you nothing, that can save you thousands of dollars. Okay? So let's go back to this one. If it takes him 10 days to get a motor, I told him, I said, look, Lowry, we got to shut this down. He said, there's no way we're shutting this pump down. If we shut it down, we're going to have to, it costs $35,000 a day the plant's making. There's no way we're shutting it down. I said, okay, it's up to you. I can take the horse and take him to the water. I can prove to him it's clean, clear, cool, refreshing water, but I can't make him drink it. Same thing. I said, Lowry, here it is. Here's the evidence of a crime, if you will. We've got 5, 6 indicators we got a problem here. Either you make a decision or that motor's going to. I guarantee you it will cost you 7 to 10 times more money if you let it make the decision. And I can prove that to you. How many of you have disc brakes on your car? Everybody. How many of you have that little cheaper on those brake pads that when that brake pad gets worn, that little cheaper starts rubbing on the rotor and you hear that squeal? That's telling you it's time to replace them. So we ignore that. It breaks off. A few months later, now when we hit the brakes, it jerks to the right and you hear metal on metal. If you would have fixed them when the cheaper told you to, you could have done it yourself for about $20 and some time. Now that you've let it go as long as it has and it's worn on that rotor, now you have to replace the rotor because they don't turn them anymore. You have to put the new pads on. You probably need to realign it because it's jerked to the right so bad. So you basically took a $20 job and turned it into $400. Yes? Is that what they call it, thing, a cheaper? Yes, a cheater. A cheaper. Yeah, it's cheaper if you fix it yourself, right. Okay, good point. I'm going to use that. Okay, so we look at this motor and apply the same thing. He said, we ain't shutting it down. I said, all right, we won't shut it down. Let's let it run to failure. That's what he says we're going to do. Okay, let it run to failure. When it runs to failure, the plant makes $35,000 a day and it takes 10 days to get a new motor. Right off of the top, we're $350,000 in the hole. Straight away. Okay? The cost of the new equipment, $6,000 for a motor. It's pumping a slurry, so when it locks up, it probably twists the shaft off in the pump. So now we're $25,000 for a pump. We got to pay overtime, manpower, all this stuff to get back here and get it done and fixed right. We took a $6,000 to $8,000 job and turned it into $500,000 because we wouldn't make a decision. Ladies and gentlemen, that right there is predictive maintenance. It cannot be explained any better, any way than that right there. Somebody has to make a decision. Because if you don't make the decision or somebody doesn't, it costs you a whole lot more money. It's that simple. Our job, my job, is to build the evidence of that crime. This is a crime. It's like an arson investigator. I had to build the evidence of a crime, take it to the county attorney so that he could make the decision to file charges or not. I have to build the evidence of a crime here, take it to the plant manager so he can make a decision of whether we're going to shut down and fix it or not. It's up to him. It's not my problem. I document everything. He comes back to me and says, "Why didn't you tell me about this?" I said, "Whoa, ho, ho." I did. CYOA. Okay? A prime example. Just a couple more right quick. This is a competitive noise. We want to be real careful with this. Bring that spectralizer back up. Go to the wave file and play before. I don't want to tell them what it is, so I'm oh, okay. Got it up here? Where we got it? File, wave file. Open the wave file. And it's right there before. Nope, next one down, right there. Play that one. Listen to this pump. That's pretty ugly. Okay, drag it off just a second there, Stan. I want to show them. I put the probe right there on that pump. That's where I made my recording, okay? We had a question about this earlier. What this is actually it's cavitation, okay? The pump is trying to pull the water through there faster than it can get it there. So what happens is we separate the molecules. We have a void or a vacuum space there. When that hits the impeller, it explodes, and it actually can take chips out of your impeller. It can actually eat your impeller right out of your pump. So we cannot allow that to happen. They could not hear that because this pump is about 60 feet down in the ground. I put the ultrasound on it and I heard it. How do we stop cavitation? We build pressure in the pump. How do we build pressure in the pump? Gate down the discharge. Never, ever gate down the suction. It's not getting there fast enough now. Why do we shut it down more? Okay? So on this pump, I actually took the gauge or the valve and I turned it that much. A quarter of a turn. Okay? Now play it again. After the correction was made, that would have never, ever been found without ultrasound. Never happened. Never happened. Okay? So we can drag that one off. I'd put a chain on this thing. Okay. Compressed gas surveys. How many people do them? Okay. Awesome. Let me show you something real quick. Next slide. Next slide. Run the argon. Can you just click on the one that says argon? It should load the program up. You have to bring it over here to do it. Click on that one. Aha! This is a plant in Beloit, Kansas, okay? I told this guy, I said, look, if you let me go through your plant and spend 3 hours doing a survey, if I can't show you that I can show you how to save enough money to pay for the whole program, I'll do it for free. He said, hey, let's get on that. So I spent 3 hours in his plant, okay? I found air leaks. I found argon leaks. Went through his plant for 3 hours, okay? Slide it over and show the total. $146,000 a year he was losing in compressed gases, argon and air. Needless to say, I didn't do that one for free. Okay? So, okay, you can drag that off. I just wanted to show you that one right quick because we're lost. You can just close it if you want to. Just X out of it. Can't even do that, can we? Ha! Huh? Yeah. Hold the Alt button down and hit F4. Now close it. No. Awesome. Okay. Next slide. Okay, so what I'm telling you, most people say there's no such thing as a silver bullet. I'm telling you there is. I'm telling you there is. That $146,000 savings we just seen right there, that's a silver bullet. Document it. The $500,000 pump job we seen a while ago, that's a silver bullet. Okay? Now I'm going to tell you why we document those, why we keep them. I document everything. Good ones and bad ones, okay? I keep the good ones in the front of the file drawer. The bad ones are in the back. If he wants to see them, I'll show them to him. But I ain't advertising it, okay? Now, when management comes down, which they do quite regular, they say, look, I got to cut the bottom line. Where's the first place they cut? Maintenance. Maintenance does not contribute to the bottom line. They protect it, but they don't contribute to it. So he comes out here and says, okay, I got to cut the bottom line. All you people over here, y'all still got a job. You guys are gone. You still have a job, but you're going to start doing their job too, and I ain't paying you no more money. Remember, I'm cutting the bottom line. Okay? At that point in time, the maintenance manager needs to jump up on the table and scream and holler and jump up and down and say, whoa, wait a minute. I have shown you and documented a $500,000 savings by doing the job the way it should have been done. I have done a compressed gas survey in this plant, and I showed you $146,000 in savings if you just allow us to fix the leaks. We're already at $650,000 savings right here this year. You name me another department in this plant or any plant in the world that can show you that and document it. Any other department, I don't care. Operations, they make $1 million a day? No, the plant does. They just run it. Okay? What I've just done, ladies and gentlemen, is I've turned your maintenance department into an asset instead of a liability. Management looks at maintenance and says, the only time I ever see you is you're wanting more money. That's all you ever go to management for. You walk in there with a 2-pound hammer and say, I need $50,000. They say, whoa, that's a high dollar hammer. They don't understand it unless we talk to them in numbers. So when we document the savings that we've done, those silver bullets become very important. We turn our maintenance department into an asset instead of a liability. You can't afford to lay these people off. In fact, you need to let me hire some more people so I can save you some more money. And that's what it comes down to. That $146,000 savings, Nick Mays is the manager's name. Call him if you want to. It's Agco Corporation, Beloit, Kansas. He went to management with that form, that spreadsheet. Said, I need to hire 2 people. One first shift, one second shift. I want to pay them $35,000 a year. And management says, you're out of your mind. We're laying people off. Why are we going to hire more? He said, because I'm going to have them do nothing but fix leaks in this plant. Management says, you're crazy. He said, no, wait a minute. $35,000 a year, 2 people is $70,000. We pay them $70,000. We still save $76,000 because we fixed the leaks. Management says, you know, that's right. They hired those people 4 years ago. They're still working there today. Now, they're on top of their leak system. Now, they're on top of the problem. They're leaking less than 5% of their compression capacity. So when they're not fixing leaks, they're doing other things in the plant. But they have been paid for already. That's making your maintenance department an asset instead of a liability. If we don't remember anything else that we've talked about today, please remember to think outside of the box. Please remember to ask the question, what is different and why? And please, above all, turn your maintenance department into an asset. Don't let it be a liability. Don't be a little fire department running around putting out fires. Prevent the fires. That's what it's all about. Prevent the fires. And with that, I thank you.